What you should remember about relative motion is that you probably learned the basics of relative motion in the activity center in kindergarten. In my activity center, we had a skateboard that I always pushed to the right at exactly 2 meters per second. We also had a little toy electric car, and since it was an electric car, I'm going to call it a Prius. Of course, my favorite thing to do was to have the Prius ride the skateboard. If you turned on the Prius and set it on the ground, it would also go at 2 meters per second. Of course, what I did is I put the Prius on the skateboard and have it then go at 2 meters per second on the skateboard. I bet you know what I did next. I turned on the Prius, set it on the skateboard, so it would go at 2 meters per second on the skateboard, and then I pushed the skateboard at 2 meters per second. So the skateboard's going to the right at 2 meters per second, and the Prius is on the skateboard, and on the skateboard, the Prius is going to the right at 2 meters per second. So my question for you is, how fast was the Prius really going? Well, that's obvious, you say. Clearly, the Prius was going at 4 meters per second. That basic idea that in order to get the real velocity of the Prius, you just add the two velocities, is the key to understanding relative motion. In physics, we have a simple notation to keep track of various velocities. For example, if I want to talk about the velocity of the Prius on the skateboard, or the velocity of the Prius on the board for short, that would be specifically the velocity of the Prius with respect to the board. And the notation is just VPB. That means the velocity of the Prius with respect to the board, because we know that the Prius can go at 2 meters per second, and you turn it on, you set it on the skateboard, you know that it's going at 2 meters per second on the skateboard. So we call that the velocity of the Prius with respect to the board. I told you I always push the skateboard to the right with a velocity of 2 meters per second. And so in order to be consistent, we have to say the velocity of the skateboard with respect to something. And in this case, the 2 meters per second is the velocity of the skateboard with respect to the activity center. Because the skateboard was moving on the ground at 2 meters per second, and the ground was in the activity center I was playing with. So VBA is the velocity of the board with respect to the activity center. So if I tell you the velocity of the skateboard is 2 meters per second, what implicitly I'm saying in my story is that the velocity of the skateboard with respect to specifically the activity center is 2 meters per second. Now, of course, maybe the activity center was on an aircraft carrier. I might have grown up on an aircraft carrier, and maybe the aircraft carrier was moving with respect to something. So I have to be very specific when I talk about velocities in physics. So VPB is the velocity of the Prius with respect to the board, and VBA is the velocity of the board with respect to the activity center. And what I want you to do is, I want you to guess, when I said, what is the real velocity of the Prius? What is the real velocity of the Prius? What letters do I use for that velocity? What's the notation that I should use when I say the real velocity of the Prius? Like if the velocity VPB is 2 meters per second and VBA is 2 meters per second. When I put the Prius on the skateboard and ask you, what's the real velocity of the Prius? What notation should I use for that? I'll give you a hint. It starts with a V, and it has 2 letters in the subscript of V, and the 2 letters are currently written on the screen. So when I say the real velocity of the Prius, what I really mean is what is the velocity of the Prius with respect to the activity center. I don't want to know what the velocity of the Prius is with respect to the board, because I already know that. But what I want to know is, by real velocity, I mean the velocity of the Prius with respect to the ground, or in this case, since the activity center is located probably on the ground and not on an aircraft carrier, I'm going to say the real velocity of the Prius is VPA, or the velocity of the Prius with respect to the activity center. So what you learned in kindergarten, if you want to know the real velocity of something, you just add the two velocities you already know. That's stuff that you knew in kindergarten if you played with little electric cars and skateboards. In physics, we have the relative motion equation, or VPA, that's the velocity of the Prius with respect to the activity center, equals the velocity of the Prius with respect to the board plus the velocity of the board with respect to the activity center. Now, interestingly enough, if you know the relative velocities, and by relative velocities I mean the velocity of the Prius with respect to the board, that's the velocity of the Prius relative to the board, or if I know the velocity of the board relative to the activity center, then I can find the velocity of the Prius relative to the activity center. Those are relative velocities. The interesting thing about this equation is that if I know the relative velocities of any three objects in relationship to each other, they all follow this same pattern. Basically, it could be anything, this could be particle, and this could be reference frame A, like it is in the chapter. So if I want to find the relative velocity of the particle to reference frame A, this could be, it's always going to be the velocity of the particle starting here, and it's going to always be added to some velocity that ends in A, because this relative velocity equation follows this pattern. Whatever letter's here is going to be the first letter here. Whatever letter's here is going to be the last letter here. And these two in between letters are always going to be the same. So they can be any three objects for which you know the relative velocity, and they're all going to follow, those three objects are all going to follow this pattern. So it turns out that what you learned in kindergarten was sort of this universal thing about relative motion. It doesn't have to be just a Prius and a skateboard and an activity center. It can be any three objects that you know the relative velocities of, and the letters always follow the same pattern. Namely, if you want to know the velocity VPA, you're going to add it to two velocities. One velocity is going to start with P, the other velocity is going to end with A, and they must have the same velocity in between in common. There are two more interesting features about this equation that I need to tell you about. And the first of which occurs when I do this maybe sort of obvious case. What if I turn the Prius around on the skateboard and point it in the opposite direction? So now the Prius goes 2 meters per second to the left on the skateboard. And then what I'm going to do is I'm going to push the skateboard 2 meters per second to the right while I run the Prius, and on the skateboard the Prius goes 2 meters per second to the left. You guessed it, the Prius doesn't have any velocity until it runs off the end of the skateboard. And the reason why I did that is I wanted to point out to you this important feature, is that the Prius going to the left makes it minus, and then we'd have the plus velocity of 2 meters per second of the board with respect to the activity center, but the minus 2 meters per second of the Prius with respect to the board, and so minus 2 plus 2 turns into 0, just like we'd expect. And what that means is that this relative motion equation is a vector equation. That means all vectors going to the left, they're going to be minus. All vectors going to the right, they're going to be positive. Now this has its important implications, is because it's not just a one-dimensional vector equation, it's also a two-dimensional vector equation. So also that means All vectors pointing up are going to be positive. All vectors pointing down are going to be negative. I'm going to talk about a couple two-dimensional examples in a minute, but first I have to tell you about the second feature about this equation. I just told you that the velocity of the Prius with respect to the board is minus 2 meters per second. That means that from the point of view of the skateboard, the Prius is moving to the left at 2 meters per second. Look what happens when I reverse the order of the subscripts. Now what this velocity says is this is the velocity of the board with respect to the Prius. What that means is that you have to put yourself in the point of view of the Prius and then look down at the skateboard during that motion, and from the point of the view of the Prius it looks like you're going to be stationary, and the question is which way is the board moving? And so from the point of view of the Prius, it looks like the board is moving to the right at 2 meters per second. Here's what's going on. If you're from the point of view of the skateboard, clearly the Prius is on top of you and the Prius is moving to the left at 2 meters per second. But if you're on the Prius and looking down at the skateboard, it looks to you like the board is moving to the right at 2 meters per second. So what that means is that when you switch the subscripts, it totally changes your point of view, but the only difference in the numerical answer of your relative velocity is that the sign changes. So what this means is, and this is going to be a useful trick later on, is that if you know the velocity of the Prius with respect to the board is minus 2, then you also know that the velocity of the board with respect to the Prius has to be plus 2 meters per second, because remember, this is all sort of like a point of view. So the Prius, according to the skateboard, the Prius is moving to the left. According to the skateboard, the Prius is moving to the left, but if you're the Prius, it seems to you like the board is moving to the right. And if those velocities, the only difference is one is minus 2 meters per second, the other is plus 2 meters per second. The point of view changes means that the sign changes. You just multiply by -1 every time you switch the order. Now, the reason why that's important is a lot of times is this equation has a specific order here and here. And a lot of times a problem will tell you not B with respect to A for some reason. It might tell you A with respect to B. And you're going to have to multiply that number by -1 to fit it into this equation. So that's an important trick for relative motion problems. So here's how you write it out. For all velocities, including two-dimensional velocities and three-dimensional velocities, if you know the velocity of the board with respect to the Prius, it's always going to be minus the velocity of the Prius with respect to the board. And namely, anytime you switch the order of these two subscript letters means you just add a minus sign. Here's a two-dimensional example. Let's say I have a boat whose maximum speed is 5 meters per second, and I point the boat due east and I run at 5 meters per second. What that means is the velocity of the boat with respect to the water is 5I hat. That's the velocity, VBW, velocity of the boat with respect to the water, is 5I hat. And it's I hat because I'm pointing the boat due east. Now let's say the water that the boat is in the form of a river, and the river is flowing south at 3 meters per second. So the velocity of the water with respect to the ground is going to be minus 3J hat. And I think if you're a riverboat captain, the real velocity that you want to know is really the velocity of the boat with respect to the ground. And if we follow our pattern, velocity of the boat with respect to the ground has to start with the velocity of some letter with B in front, and it has to end with some letter in G at the back, because I have to match up the front letter here has to be this, the back letter here has to be this, and they have to share the same letter in between. Alright, so I know if I want to find the velocity of the boat with respect to the ground, I'm just going to add those two vectors as vectors. Or I get the velocity of the boat with respect to the ground is 5 meters per second to the right, simultaneously going 3 meters per second south. So here's the boat. The boat by itself would move to the right like this. The water by itself would move down like this. And then together they go down and to the right. Now here's something interesting about this problem that you'll have to know for your homework, is that notice the time it takes to cross the river with your boat. Oops, let me separate the boat from the river. The time it takes you to cross the river for your boat, if the water isn't moving, it takes the same amount of time to get from one side of the river to the other side, because your boat is pointing straight east. But also, whatever that time is, let's say you could stop the river and you pointed your boat straight across the still water, and maybe it took you like 30 seconds. And then you started the river up again, it would still take you 30 seconds to get to the other side of the river. Isn't that interesting? If your boat is pointed straight across the river, it doesn't matter how fast the river's going. In fact, if the river's going really fast, it takes you the same amount of time to cross the river than if the river's going slowly. What happens is, in that really fast water will just take you downstream farther. If you just want to get to the other side of the river, notice the time it takes to get to the other side of the river is independent of the river speed. It doesn't matter how fast the river's going. The only thing is that if a river's going really fast, and the time it takes you to cross, you'll end up farther downstream than if the river's going really slow. The time it takes to get you to cross, if you point your boat straight across the river, the time it takes for you to get across the river doesn't depend on the river speed. It's just totally depends on just your boat speed. Next, I want to tell you about an important riverboat captain problem. And let's say you're on a river and the river is flowing south at minus 3 meters per second. I mean, south being minus north. So the velocity of the water with respect to the ground is going to be minus 3 j hat. And you as a riverboat captain, your riverboat can go 5 meters per second, but you would like to cross the river straight across. Like you're here at this, and you want to go, you're a riverboat captain, maybe there's a city over here, and you want to take your passengers directly across the river to a city over here. And the question is, which direction should you point your boat so the path of the boat is directly across the river? That means, notice that if you point your boat straight across the river, you're going to go down to the right. But how should you point your boat so you'll go straight across the river? And here's how you should think about it. The velocity of your boat with respect to the ground can be some number I hat that we don't know yet. But if you're going straight across the river, it has to be 0 j hat. So remember from our equation, the velocity of the boat with respect to the ground has to be the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. And in order to go straight across the river, we have to have 0 j hat for the velocity of the boat with respect to the ground. So it must be that whatever the velocity of the boat with respect to the water is, and we don't know the x component, but for sure the y component has to be plus 3 j hat, exactly canceling out the y component of the water. So I know that the velocity of the boat with respect to the water has to have a plus 3 j hat component because the water is going south at 3 meters per second, and I want my boat to cancel that out exactly. So the boat has to have a vector component going north at exactly 3 meters per second to cancel out the fact that the water's going south at 3 meters per second. And so I have to make a little vector diagram. I know that my boat can go 5 meters per second, and I have to angle it in such a way so that it's got a north component of plus 3 meters per second, and which that means is that, well, this I picked specifically, it's a 3, 4, 5 triangle. So that means that this angle is 37 degrees. Now, if it wasn't a 3, 4, 5 triangle, all that you would do is take the arc sine of 3 divided by 5, because this angle theta is the opposite side divided by the hypotenuse. And so if you take inverse sine of 3 divided by 5, you'll get this angle theta. So interestingly enough, we know that the horizontal or x component of the boat's velocity is 4 I hat, and notice how this is the actual velocity now with respect to the ground. This got to be 4 I hat, right? Because this component is going to cancel out the river velocity, leaving only the riverboat going straight across the river at 4 meters per second, and totally comes out of trig. So what happens is, when you do this, the boat would be going up at this angle. It would be going up at this angle, so it would have a 4 meter per second horizontal component and a 3 meter per second vertical component. But at the same time it's going up at this angle, the river is carrying the boat down at 3 meters per second, so the boat actually goes straight across. Right? So we're using vector, we're using vector components to cancel out. So here's the boat. If the river water wasn't moving, it'd be moving up at 4 meters per second to the right and 3 meters per second up. But at the same time, the river's going down 3 meters per second squared, and the vertical components exactly cancel out, and that leaves only the 4 meters per second of the boat, and it apparently goes straight across. And so notice that it's kind of an odd thing, is that the river's going south, the boat's actually moving straight across the river, but the boat's kind of pointed upriver at, in fact, 37 degrees. And we could know that based on these particular velocities. So, the other thing is, what if we want to calculate how long is it going to take us to cross the river? If we know the width of the river, the velocity that we should use is just the x component of the velocity. I think that's pretty cool. The other thing I would like to tell you about this is that, clearly, if you want to cross the river in the least amount of time, and you don't care about where you end up on the other side, what this angle should be, it should be 0 degrees. You should point your boat straight across the river. That way you can use all your speed to get from this side of the river to the other side of the river. And it doesn't matter that, if you don't care, it takes all your speed to go from one side of the river to the other side of the river. If you point your boat straight across, it doesn't matter that the water's moving downwards. You're just going to go from here to here on the water, while at the same time the water can be moving up and down. It totally doesn't matter what time it takes. If the water's moving, in the case where you just want to get from one shore to the other, the fastest way across is point your boat straight across the river, and sure, the water's going to carry you downstream a little bit, downstream. But if the goal is to get to the other side of the river, use all your velocity to go across the river. It doesn't matter how fast the river goes. Alright, I want to finish this with a hint about your first problem on the relative motion worksheet, is that there's going to be a case where you point your boat upstream and it tells you a given time, and then you point your boat downstream and the boat's going downstream. And the only difference is, in the upstream case, you know that the boat with respect to the water is some unknown value x in the positive j direction, right? But if you point your boat downstream, and your boat's going downstream, the boat with respect to the water is that same unknown value x, but it's going to be negative, right? So when the boat is pointed upstream, it's the velocity of the boat with respect to the water will be 0 I hat plus x j hat. But if the boat is pointing downstream, its velocity with respect to the water only will be 0 I hat minus x j hat. And then you can use the relative motion equation to somehow determine what x is using algebra. And that's how you're going to start the first problem on the homework. And then it's going to be more stuff working with the relative motion equation, and in not just 2 dimensions but also 3 dimensions, so it'll be just that much more exciting.